Hello Math 119 students. Today we're making a video on section 6.5 in Hawks, which is about the normal approximation to the binomial distribution. So in some cases you can use a normal distribution to approximate a binomial distribution problem. However, you can't always do this. The larger the sample size, usually the more accurate your results will be. So here we have some examples. We have 4 binomial distributions, and you can see the sample size increases as we go along. So with a small sample size, you can see this really doesn't look too much like a normal distribution. So this one probably wouldn't qualify. Then when you get to a sample size of 10, it starts to look better, more like a bell shape. Then when you get to 25, it looks fairly bell-shaped, and 50 looks even better. Now the criterion is you want to have NP greater than or equal to 5 and NQ greater than or equal to 5. Both true at the same time. So you can see when you have the small sample size, NP and NQ are both less than 5, so this one wouldn't qualify. And then with n equals 10, NP is not greater than or equal to 5, so that wouldn't qualify. But with the two on the bottom, 25 and 50, both NP and NQ are greater than or equal to 5, so each of these would qualify, which means you should get fairly accurate results if you use a normal approximation to approximate a binomial problem for these two distributions. Let's go to page 2. So page 2, we have a binomial distribution, n equals 40 and p equals 0.5. So this one would qualify because NP and NQ are each equal to 20. Now, in the first example, we want to, well, let me mention this first. So that what we have here is we've overlaid a normal curve along with the binomial histogram. And the normal curve has a mean of the n times p. Remember, for the binomial distribution, the mean is np. So NP would be 20. So we have a normal curve with a mean of 20. And the standard deviation for the binomial distribution is the square root of NPQ. So the standard deviation for this binomial distribution would be the square root of 40 times p, which is 0.5, times q, which is 0.5. So it would be 3.16 would be the standard deviation for the binomial. So this picture shows a normal distribution with a mean of 20 and a standard deviation of 3.16. So you can see it fits fairly nicely here. It looks fairly close to the shape of the histogram. So now if we want to approximate, we can use the normal curve to approximate the probability that x equals 18. The exact probability that x equals 18 would be the area of bar 18 on the histogram. So since the width of all these bars are equal to 1, it would be the height of bar 18, which would be about a little bit more than 0.1. Now, if we want to use the normal distribution to approximate the probability that x equals 18, what we would do is we would find the area under the normal curve. So the area under the normal curve from 17.5 to 18.5. So it would be this area under the normal curve right here. From here to here. And it would be the area under the normal curve. Now, the second problem is, what if we want to find the probability that x is less than or equal to 18? So the probability of 18 or less. So the exact probability would be the area of bars 18 down to 0. But if we want to use the normal approximation to approximate it, then we would find the area to the left. Bar 18 begins at 17.5 and ends at 18.5. So what we would do is we would find the area under the normal curve to the left of 18.5. Okay? So for this example, let's compare the answer with the exact answer. So here's what the exact answer would be. We can use binomial CDF. So the exact answer, the probability of 18 or less successes, would be 0.3179. And the approximated answer would be the area under the normal curve. So we can use normal CDF. So for the lower, I'll put 0. And for the upper, 18.5. Okay, the mean was 20, and the standard deviation we calculated, it was 3.16. So the approximated answer would be 3.175. You can see the two answers are fairly close. Okay, now notice in both cases we added or subtracted 0.5. So we took 18 and we added 0.5. This is called using the continuity correction factor. The fact that to use the normal distribution to get a more accurate answer, in this problem here we added 0.5 and we took the area to the left of 18.5. This is because bar 18 doesn't begin at 18, it ends at 18.5. So that's the reason why we added 0.5. So using the continuity correction factor, you're either going to want to add or subtract 0.5. So page 3 on the handout shows you whether or not you should add or subtract 0.5. And so let's say you have a binomial distribution, you want to find the probability of at least 235. So that would be 235 or more, but you want bar 235 to be included. So you'd find the area to the right of 234.5, so that bar 235 is included. And then if it was more than 235, it wouldn't include 235, so you'd find the area to the right of 235.5. So this table here shows all the possible types of problems you could have, and whether or not you want to add or subtract the 0.5. It also shows a nice diagram here. So I'll leave this for you in case you want to use it for your homework. Page 3. We got 2 more problems to do. So let's complete these 2 problems. This one is actually already solved for you, but we'll read it anyway and look it over. So it says 62% of adults in the U.S. have an HD TV in their home. So that would be P equals 0.62. You randomly select 45 adults, so that will be your sample size, and ask them if they have an HD TV in their home. What is the probability that fewer than 20 of them respond yes? Okay. So we're going to use the normal approximation, and it says, can we use the normal approximation? And this is for a different book, but let's check it. So we have n equals 45 and P equals 0.62. So NP would be, and then N each of these has to be greater than 5. This one's 27.9. Oh, not 0.62 here. This would be 1 minus points. Q would be 1 minus 0.62 would be 0.38. So this should be 0.38. Okay, so that's 17.1. So NP and NQ are greater than or equal to 5. So the answer is yes, we can use the normal approximation. Okay, and then it says we need to apply the continuity correction factor. So fewer than 20 would be 0 through 19. So we don't want bar 20 to be included. So we would find the area to the left of 19.5. Okay, so then for this distribution, the mean would be 27.9 and the standard deviation would be 3.26. So the area under the curve below 19.5 would be, for normal CDF, the lower would be 0, the upper would be 19.5. This will give us the area to the left of 19.5. The standard deviation is 27.9 and the standard deviation is 3.26. So we would get 0.0050. Now, just to compare with the exact answer, we'll calculate the exact answer for comparison. We can use binomial CDF. So 45 is the number of trials. P would be 0.62. And then X would be 19. It says fewer than 20, so X would be 19. So that's what I have. And it says 0.0056. So that's pretty close to the approximated answer. It's within 6 ten-thousandths of the exact answer. Okay, the last problem I have is if we have 100 births, what's the probability more than 55 girls being born? So we'll assume P equals 0.5 and then N is 100, the sample size. So NP and NQ are both equal to 50. So it satisfies the criterion for using the normal distribution. Now we need the mean and standard deviation. That would be the square root of 25, 5. So our standard deviation would be 5. So we want the probability of more than 55. Okay, more than some number does not include that number. So more than 55 would be 56 or more. So we'd want to begin, if using the normal distribution, we'd want to begin at 55.5. So we can write it like this. And then we will have a normal curve with a mean of 50. And we'll want to find the area to the right of 55.5. So we can use normal CDF. And the lower will be 55.5. The upper, I'll just make it 100. That's the maximum you could have. The mean is 50. And the standard deviation is 5. So this is what I have. And the answer comes out to be 0.1357. The approximated answer. So that's our answer. And it should be fairly accurate. It won't be exactly the same as using the binomial distribution, but it should be. The other examples where we had fairly accurate results. So this one's probably fairly accurate as well. So that's it for this handout.